In this screencast, I'm going to talk to you guys about ocean acidification. Yeah, it sounds bad, and it is bad. All right, so remember, global warming is primarily caused by anthropogenic carbon dioxide production. All right, and as CO2 levels increase in the atmosphere, we're encountering, and that's causing global warming. It's causing another problem too, which is ocean acidification. Now, um, sorry, got a lot of burps tonight. So sorry. So like other gases, like oxygen, CO2 is soluble in water, right? So it dissolves into the ocean. And it turns out that the world oceans can, like we said before, it's the largest reservoir of carbon dioxide on the planet. It basically has 16 times more carbon in it than all life on Earth does. And it's got 60 times more than the atmosphere had prior to the beginning of the Industrial Revolution. So it is this vast carbon sink. And what happens is, what happens to this carbon dioxide when it gets in the ocean is something that we need to take a look at because it's changing the chemistry of the ocean. Now, remember, CO2 both dissolves into, we say diffuses into the ocean and it diffuses out of it. So we call this the physical carbon pump. And so the idea is at the poles where the water is very cold, the water can accommodate more carbon dioxide. So it sinks into the ocean there, travels along the conveyor belt. And then as it warms up eventually, it gets to warmer waters and then it gets released back up. And so there's this cycling of carbon dioxide through the oceans in this sense. But the main takeaway here is cold water absorbs more carbon dioxide. Warm water either releases it or at least holds less of it. Now, the thing is, when this carbon dioxide goes into the ocean, we've said before, it doesn't just sit there. Somewhat it does, but a lot of marine organisms, corals, mollusks, and coccoliths, these little phytoplankton, they take that carbon dioxide that dissolves in the water, and they use it to make a substance called calcium carbonate, which is a non-water soluble, it's not soluble in water substance, basically chalk, seashell material, coral material. And since it doesn't dissolve in water, it's ideal for making rigid structures like the skeletal structure of a coral colony or the shell of a clam or the internal skeleton of one of these coccoliths. But in the process, these life forms that make these calcium carbonate shells and skeletons, they sequester a significant amount of the carbon dioxide that goes into the ocean. All right, and then they store it for a long time, for millions, hundreds of million years, as part of the slow carbon cycle. But there's a problem, and what happens is that the rate at which we're now putting carbon dioxide into the air matches the rate at which it's going to the ocean. So if you look here, this is a pretty interesting graph. This is what's called the Keeling Curve. Now remember, it goes up and down. It's carbon dioxide. We've talked about it before, but it's worth mentioning again. Basically, carbon dioxide levels go up in the northern hemisphere, like say in the monitoring station at Mauna Loa, Hawaii, goes up in the winter months when productivity is low, and it goes down in the summer months when productivity is high. So we get this little wiggly curve. But if you notice, it just goes up, 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 up. All right. And actually now it should be up close to 400 if we were to extend it up to where we are today. This one stops around 2010, but it's up around 400 now. And what we see is the concentration of carbon dioxide in the ocean has basically matched that trend. And basically what's happening is we're adding carbon dioxide to the ocean at a faster rate in which these organisms are able to sequester it. So the level of carbon dioxide in the ocean is increasing. Well, here's where the problem comes in with ocean acidification. Because when carbon dioxide mixes with water, it doesn't just stay as carbon dioxide. It undergoes a chemical reaction and it forms a thing called carbonic acid, H2CO3. So this is a hydrogen ion here, right? And so basically, it's a weak acid, meaning it doesn't completely dissociate, but it makes hydrogen ions. So when you add hydrogen ions to water, what happens? The pH goes down. It becomes more acidic. And so all this carbon dioxide going in and not getting sequestered fast enough by these shelled organisms is causing the pH of the oceans to change. And now, don't let the name fool you. It doesn't mean that the ocean is now acidic. It just means that its pH is moving in the acidic direction, is dropping. Okay, so if you look here, the pH of the ocean is, at least when this graph was made, was about a little bit over 8. It started out at probably here, in 1990, about 8.13. Okay, so it's been dropping over time as we add hydrogen ions to the ocean by virtue of making carbonic acid out of carbon dioxide. So prior to the Industrial Revolution, the pH of the ocean, it can be determined from paleo evidence, was 8.2. Today, it's around 8. And by the end of the century, it should be closer to 7.7. Still not acidic, but here's the problem, is that when you change the pH of the ocean, you unfortunately change the ability of organisms to manufacture CaCO3. See another positive feedback loop coming? As you put more carbon dioxide in the ocean is less able to take it out in the form of calcium carbonate, because what happens is carbonic acid reacts with this and it turns it into calcium hydroxide. Let's see, it turns it into calcium. Oh, I forget what my anion is here. But anyway, it's going to basically turn this into CO2 plus water plus some calcium compound. Sorry, I forgot what it was. But basically, this is dissolved by acid. And as I put hydrogen ions in the ocean, I basically break this down. And that's a problem because shell organisms can't make their shells if the pH is too low, which in some places it definitely is. And so we find then is that there are fewer tons of shell material being produced as a consequence of this diminishment of pH. Now, the other thing that happens is we're not storing as much carbon as we used to in calcium carbonate. So that means that there's more carbon dioxide building up. Like I said, there's a positive feedback loop here. Now, this isn't just hypothetical. I mean, this is already happening in places. So, for instance, where I live is a place called Kitsap County, Washington. We have a saltwater body. It's a natural body waterway. It was known as a fjord, a flooded glacial valley. It's called Hood Canal, even though it's not really a canal. Anyway, Hood Canal has been known for 100 years as being this amazing oyster fishery. Okay, great oysters, right? So many people make their money raising oysters there. Well, what's happened now is the pH has already gotten low enough that they can't grow oysters from what was called oyster spat. In other words, like when a fertilized oyster larva attaches to a rock, it's not able to start making shell. That initial shell just won't form because the pH is already so low. So what they have to do is these companies, which always were able to make their own oysters just by letting their oysters spawn. Now that oysters try to spawn, nothing happens. They actually had to bring in what they call starts, or little tiny yearling oysters, and let them start to grow because the water there is already acidified too much. And this is not the only place in the world that's happening. It's also affecting coral reef formation. Has been observed to be slowed by this process. Keep in mind that these phytoplankton, these coccoliths, are a major source of the world's oxygen supply. So this is a very concerning problem. All right, I'm just going to use some of my amazing Samson artwork to walk you through this idea here. Okay, so here you go. This is a coal plant, if you couldn't tell. This is a coal-fired power plant making pollution, which contains carbon dioxide. So we're putting carbon dioxide in the air. We're basically taking coal out of the ground where it's been sequestered. The carbon has been sequestered, turning it into carbon dioxide, putting it in the atmosphere as a greenhouse gas. As this greenhouse gas piles up, it diffuses into the water. So now CO2 leaves the atmosphere and goes into the water. Remember, the ocean is the world's largest reservoir of carbon. As it goes into the water, the CO2 is going to react with water to form carbonic acid, H2CO3, all right, which is basically hydrogen carbonate. And so before we started doing this, the pH of the ocean was about 8.2. But now we find is that pH is going down. Now what ideally would happen is as CO2 goes in and forms the hydrogen carbonate, these marine organisms, corals and mollusks and coccoliths, would take that and convert it into calcium carbonate, which is not water soluble. And so that carbon would end up at the bottom of the ocean in these shells, either as coral or clam shells or the little tiny rain of coccoliths sinking to the bottom. And that would sequester much of this carbon dioxide. So as carbon dioxide comes into the ocean, instead of staying in the ocean and making the ocean acidic, it turns into calcium carbonate and sinks to the bottom. What happens is, as the CO2 levels go up, look at my artwork. As the CO2 levels go up, more of this is coming in faster than the organisms can sequester it. And so what happens is now all this carbon dioxide is turning into carbonic acid, so much so that the shells are having a hard time forming, so they're not able to sequester it at the same rate they used to. And so as a consequence, what happens is um, there's a increased concentration of CO2 in the atmosphere, which makes the atmosphere warm. And when the atmosphere gets warm, then the ocean gets warm. And remember, a warm ocean has a harder time absorbing carbon dioxide, which makes the atmosphere even hotter, and so on. All right. Thanks for watching. Again, I'm sorry that all this gloom and doom. I'm just glad this is the last 2 weeks of school that we've had to deal with the gloom and doom aspect of this course.